Hello and welcome to the live stream here at o'kellychemistry.com. My name's Ivana O'Kelly and thank you for joining me. In this live stream, we'll start off by drawing some basic molecular structures using a method that's as easy as ABCD. Together, we'll do a deep dive into VSEPR theory, where you'll be able to investigate a 360-degree view of a range of molecules directly on your screen. And finally, you'll discover how to draw perspective diagrams. Perspective diagrams are what we use to represent 3D molecules on paper. I'll have some checking quizzes along the way for you. These will be interactive quizzes accessed directly through the course here at o'kellychemistry.com. As a reminder, if you do have any questions during the live stream, please make sure you go ahead and enter them into the chat. Ladies and gentlemen, let's get started. So make sure you have access to a periodic table, you have some pen and paper, and you have a calculator at hand in case you need to make some simple calculations. So this is the first part of our live stream where we're going to look at how to draw some basic molecular structures. And I'd like to start off with asking you a question. So, what is the difference between a bonded pair of electrons versus an unbonded pair of electrons? So on the screen, I have two diagrams here. The first one on the left is carbon dioxide, CO2. On the right-hand side, I have ammonia. So as you can see, a bonded pair of electrons will be found between the different atoms in the molecule. The unbonded pairs of electrons will be found either on the outside atoms or on the atoms in the center. If the electrons are found on the center, so if a pair of electrons are found in the center, we call those lone pairs. So what are these four steps that I've been talking about? The first step is that we're going to discover how many electrons each atom in the molecule needs. That's based on the octet rule. And then we're going to determine how many electrons they actually have, which are their valence electrons. And then the difference between these two will tell us how many bonded pairs there are between the atoms in the molecule. And then the difference between our valence electrons is what we have, minus our bonded pairs. That's going to tell us how many unbonded pairs of electrons we're going to have in our molecule. There's two other points we need to keep in mind, that our least electronegative element is always going to be found in the center, and hydrogen is always going to be on the outside. So let's do a quick recap of our valence electrons. So using the periodic table, this is group 1, and everything in group 1 has one valence electron. Everything in group 2 has two valence electrons. Our transition metals are going to have variable valencies. Over here on the right-hand side, everything in group 3A or group 13 will have 3 valence. Everything here will have 4 valence electrons. And moving on, we have 5 valence electrons. Group 16 will have 6 valence electrons. Group 17 will have 7. And our noble gases are also called the inert gases because they have a full set of electrons in their outside shell. So they have 8 valence electrons. But obviously remember that helium will only have 2 valence electrons because it's in period 1. It only has a 1s orbital. So now we're going to look at how to draw carbon dioxide. That's our very first molecule. So in column A, we're going to list the elements that we have. So we have carbon and we have oxygen. So each atom of carbon is going to require 8 electrons to be stable. Each atom of oxygen is also going to require 8 electrons to be stable. And because we have 2 of them, we're going to times that by 2. So again, we're focusing on how many electrons each atom in the molecule is going to require. So when we multiply and add all that up, we'll end up with 24 electrons. Column B is dealing with our valence electrons. So we list our elements, carbon and oxygen. Carbon has 4 valence electrons, oxygen has 6, and again we will times it by 2. So when we add all of that up, we will get 16 electrons. Now for column C, it's going to be A minus B, so the electrons that we need minus our valence electrons, giving us our bonded pairs. So that will be 24 minus 16. That's going to be a difference of 8. So that means that we have 8 electrons that are involved in bonded pairs. So ultimately that means that we're going to have 4 lines between our carbons and our oxygens. The last column represents the unbonded pairs. So that's going to be 16 minus 8, and that will give us 8 electrons. So I'm going to draw out my 8 electrons. Now, which of the two elements, carbon or oxygen, is going to go in the center? Carbon is going to go in the center because it is the least electronegative, meaning it's the furthest away from fluorine on the periodic table. So we have carbon, and then we have our oxygens on the outside. So looking at column C, we have 4 bonded pairs. So we'll start with one either side and then we'll go back. And now what we can see is that carbon, right now the way that we've drawn it, has access to 8 electrons, 4 from its own and 4 shared between the 2 oxygen atoms. So now looking at column D, we have to fill in our unbonded electrons, and they're going to go on the 2 oxygen atoms. And there we have it. We've drawn our first basic molecule, carbon dioxide. So the next molecule we're going to draw is a molecule of methane. So again, we list our elements, carbon and hydrogen. Carbon needs 8. Each atom of hydrogen needs 2. We times that by 4, and that will give us a total of 16 electrons. Looking at our valence electrons. So our valence electrons are column B for each of the elements. Carbon has 4, hydrogen has 1, and we will times that by 4. That gives us a total of 8 electrons. Now for column C, we're going to write down A minus B, and that will be 16 minus 8. So that gives us 8. So we'll have 4 bonded pairs. And for column D, we have B minus C. So it will be 8 minus 8, giving us 0. So in a molecule of CH4, we have 0 unbonded pairs. Our carbon goes in the center. Hydrogens are always going to be on the outside. So 1, 2, 3, 4. And then we'll draw our bonded pairs between our atoms of our molecule in CH4. So that's how we draw it. Our next is going to be water. So column A is hydrogen and oxygen. Each atom of hydrogen needs to have 2 electrons, and we'll times it by 2 because there are 2 atoms of hydrogen. Each atom of oxygen needs 8 to be chemically stable. So when we add that up, we will have 12 electrons. For column B, again, remember these are our valence electrons. So we list our elements, hydrogen and oxygen. So hydrogen has 1 valence electron, oxygen has 6. So we will times our hydrogen by 2 because we have 2 atoms of hydrogen. We only have 1 oxygen. So that will give us a total of 8 valence electrons. Again, for column C, the difference between our need and our have, A minus B, that is 12 minus 8, giving us 4. So we will have 2 bonded pairs in a molecule of water. And then in our last column D, it will be B minus C. So it will be 8 minus 4. So that means that we have 4 electrons, or 2 pairs of unbonded electrons. So oxygen will go in the center. Hydrogen will be on the outside. We'll draw our bonded pairs between our oxygens and our hydrogens. As we know, hydrogen only needs 2 electrons to be chemically stable. So the unbonded electrons are going to go on our central atom, oxygen. So we'll keep that in mind as we move on. This would represent 2 lone pairs of electrons on our central atom of oxygen. Moving on to NH3. Again, list your elements, nitrogen and hydrogen. Nitrogen needs to have 8, hydrogen needs to have 2, and we have 3 atoms of hydrogen, so we'll times that by 3. That will give us a total of 14 electrons. Our valence electrons for each atom in the molecule, nitrogen has 5, hydrogen has 1, but we're going to times that by 3. That gives us a total of 8 valence electrons. A minus B, 14 minus 8, giving us a total of 6 electrons involved in a bonded pair. So that's 3 lines we will draw. And then for D, B minus C, 8 minus 6, giving us 2 electrons, or 1 pair of electrons that will not be bonded to anything else. Nitrogen is in the center, it's the least electronegative. Our hydrogens are on the outside, 1, 2, and 3. We'll fill in our bonded pairs of electrons, and then our unbonded pair on the central atom will satisfy the octet rule. Each atom in this molecule has their full set of electrons to be chemically stable. So that's a molecule of ammonia. So now I want to show you how to draw a polyatomic ion. Now, how do we know this is a polyatomic ion? We see NO3 and we see a negative sign up here. So what I would urge you to do is, as soon as you see a negative sign, go ahead and place it into column B. So the charge is -1, so that means that we have 1 valence electron based on our charge. So back to A, nitrogen and oxygen. Nitrogen needs to have 8. Oxygen also needs to have 8, but we have 3 atoms, so we'll times that by 3. That will give us a total of 32 electrons that are required in a molecule of NO3-, which is our nitrate ion. And then our valence electrons, nitrogen and oxygen. So nitrogen has 5, oxygen has 6, times that by 3, plus the 1 for the negatively charged polyatomic ion. So when we add that up, we get 24 valence electrons. Now, just as a catch, if you find that you have an odd number, make sure that you have included that charge. That can be useful as a tool to help you out. For C, we're going to do A minus B. So 32 minus 24, giving us a total of 8 bonded pairs. So 1, 2, 3, and 4. And then for our unbonded electrons, it will be B minus C. So B is 24, C is 8. So we're going to have 16 electrons. I'm not going to draw them out, I'll just put them in a box there, but we have 16 of them. So nitrogen and oxygen, there are 2 elements that are present here. So which one is going to go in the center? The nitrogen will go in the center. Our oxygens will go on the outside. And then we're going to fill in our bonded pairs. So we'll go 1, 2, and 3. But we actually have to have 4 bonded pairs. So this is our clue that this is a double bond. So the double bond can be placed either side of the nitrogen with any of those oxygens. This is a term called resonance, which is covered in another video. I'm going to put it on the first one. And then I'm going to go ahead and fill in my unbonded pairs. So 1, 2, 3, 4, 5, 6. It already has 2. 1, 2, 3, 4, 5, and 6. And the first oxygen atom on the left, it already has 4. So 1, 2, 3, 4. So those unbonded electrons add up to 16. And because this is a polyatomic ion, you are going to be required to put a square bracket around it with the negative charge on the outside. So that is how we draw a polyatomic ion for nitrate. So NO3 minus. So just to recap, our 4 steps, A, B, C, and D. The electrons that we need are A, so that's based on the octet rule. B are our valence electrons. So the difference between A minus B is going to give us our bonded pairs, and then B minus C is going to give us our unbonded electrons. Remember that the least electronegative element will always go in the center, and hydrogens are always on the outside. So ladies and gents, I hope that helped with helping you draw some basic molecular structures. If you'd be so kind as to go to the checkpoint lesson quiz 1.1. So now that you've taken the first quiz and I've looked at the data, pretty good, we're going to go ahead and we're going to start lesson 1.2. So the question here is, what does VSEPR stand for? Well, it's an acronym and it stands for valence, shell, electron, pair, repulsion. So the valence electrons are found in the outside shell furthest away from the nucleus, and electrons are negative. So if you have a pair of electrons, they're going to cause a repulsion, which is then going to have an impact on the molecular shape or the shape of our molecules. So this time, what is a bonded pair of electrons versus a lone pair of electrons? So the bonded pair will be shared between the atoms in the molecule. The lone pair is an unbonded pair of electrons, but will be specifically focusing on the central atom. And collectively, that's going to impact our what we call the electron domain geometry and our molecular geometry. So the word domain can either be a single bond, a double bond, or a triple bond. Each one of these will be the equivalent of one domain. And then a lone pair, which is found on our central atom, that's an example of one domain. So looking at the electron domain geometry, it's predicted based on the number of bonded pairs of electrons and the number of lone pairs on the central atom. The molecular geometry is affected by the lone pairs, but the name of it will be based on the number of bonded electrons. So I'm going to switch over and we're going to show you a molecule of carbon dioxide. So if you missed the first part of the live stream, up here on the left, this is how we figure out how to draw a molecule of carbon dioxide. So taking a minute to look at this molecule of carbon dioxide, our carbon is in the center, our oxygens are on the outside, and there are 2 double bonds, one on one side and one on the other. So the total groups of electrons that surround the central atom of carbon dioxide is 2. So when a molecule has 2 groups of atoms surrounding a central atom, we call that linear, L-I-N-E-A-R. And the bond angle is referencing between the oxygen atoms. So it's either side of the central atom. So that bond angle, they're in a straight line, is 180 degrees. The number of bonding pairs will be 2. The number of lone pairs on the central atom will be 0. And because there are 0 lone pairs on the central atom, its molecular geometry will also be linear. So that is a molecule of carbon dioxide. So the next one we're going to look at is our polyatomic ion. So this is NO3, called the nitrate ion. So if we look at it and answer the first question, the total number of groups of electrons that surround the central atom, we have single bonds here, and we have a double bond between this oxygen and the nitrogen. So that's going to give us a total of 3 domains. The electron domain geometry for that is going to be trigonal planar. And the bond angle is going to be 120 degrees. Now, how many bonding pairs exist between the central atom and the outer are going to be 3. We have 0 lone pairs. So the molecular geometry is also going to be trigonal planar. So that is a molecule of nitrate, polyatomic ion. So our next one, I want you to look at it. There's a central atom of sulfur. There are 2 oxygen atoms. One is a single bond, one is bonded by a double bond. And this here at the top is a lone pair. So this is what we use to represent a lone pair in these kits. It's going to go up there. And in this space, so this is a region where we will find a pair of electrons. They're not bonded to anything else. They are unbonded. So that's why they get called a lone pair, because they're on the central atom. So filling out the chart here on the screen, the total number of groups of electrons that surround the central atom are 3. The electron domain geometry is trigonal planar. The bond angle is going to be less than 120. So remember, we referenced VSEPR theory. So that pair of electrons in the lone pair are basically pushing those oxygen atoms further away. And then by doing that, they're going to cause those oxygen atoms to be closer together. So that's why it's less than 120. The number of bonding pairs will be 2. The number of lone pairs on the central atom will be 1. So when we have a lone pair, our molecular geometry is going to be different than our electron domain geometry. So the name given to this is angular or bent. So ANGULAR. So that is a molecule of sulfur dioxide. Next molecule. If you look at it, there's a central atom, and there are 4 atoms on the outside. So this is CH4. And you can investigate and see that there are 4 groups of electrons surrounding the central atom. So when we have 4 that surround the central atom, the electron domain geometry is called tetrahedral. And remember that tetra means 4. And the bond angle is going to be 109.5 degrees. The bonding pairs will be 4. The lone pairs will be 0. So the molecular geometry will also be tetrahedral. So that is a molecule of methane. Switching over, here we have NH3. So if you look at it, you see that there are 3 hydrogens and there is 1 lone pair. So the total groups of electrons will be 4. The electron domain geometry, because there are 4 domains, is tetrahedral. The bond angle is going to be less than 109.5. Again, that lone pair is causing those hydrogens to be pushed away because it has a greater power. So the bond angles between the hydrogens will be less. The bonding pairs are 3. The lone pairs are 1. So its molecular geometry is trigonal pyramidal. So that is a molecule of NH3. And moving on to water. So take a second to count the number of domains that surround the central atom. There's 2 single bonds and there are 2 lone pairs. So that gives us a total of 4. So the electron domain geometry is tetrahedral. The bond angle, when we're talking about water, it's very specific, and you need to know this. It is 104.5 degrees. The bonding pairs are 2. The lone pairs are 2. So the molecular geometry is bent. So this is our deep dive into some molecules. So what I want to do now is just review what we've looked at. So we've looked at molecules where we've had 2, 3, and 4 domains surrounding our central atom. So if something is linear, it's going to have 2 bonded pairs and 0 lone pairs. If something is trigonal planar, it will have 3 bonding and 0 lone pairs. If it's angular or bent, could be referenced also, it will have 2 bonding pairs and 1 lone pair. If it's tetrahedral, it'll have 4 bonding and 0 lone pairs. Trigonal pyramidal will be 3 and 1. And bent will be 2 bonding pairs and 2 lone pairs. So this is kind of halfway through this lesson. So make sure that you are able to identify the bonding pairs of electrons and the lone pairs of electrons, so that from that you can determine what is the molecular geometry of a molecule. And notice that if there are 0 lone pairs, the molecular geometry and the electron domain geometry will be the same. So here is a summary chart for you. This is also available in the materials section of this course. So we're going to move on to part 2. So part 2 of this lesson, we're going to deal with electron domains with 5 and 6. So this is our first molecule, and we're going to look at 3D. So we have phosphorus in the center, and we have 5 chlorine atoms on the outside. So there are a total of 5 domains. So the name that's given to this is trigonal bipyramidal. The bond angle, we actually have 2. So we're going to have 90 degrees and we're going to have 120 degrees. So if you look at the molecule here, there's a 90 degrees. And then down here, all right, between these two are 120 degrees. So again, if I move this, you see 90. And look at the bottom and you see 120 degrees. The bonding pairs will be 5. The lone pairs will be 0. And the name that's given to the molecular geometry, because there are 0 lone pairs, it's also going to be trigonal bipyramidal. So our next molecule is going to be, we're still dealing with 5 regions around the central atom. So we have 4 bonded pairs. You see them there, they're orange. And we have 1 lone pair. So the number of groups that surround the central atom is 5. The electron domain geometry is trigonal bipyramidal. And the bond angle for this is also going to be 90 and 120 degrees. The bonding pairs are 4. The lone pairs are 1. So again, because we have a lone pair, its molecular geometry is going to be different. So if you look at this molecule here, let's wait for it to come around. And if I do it this way, when it moves side to side, that might be a clue to help you remember the molecular geometry. It is a seesaw. That's where the name comes from. So again, we're introducing a lone pair. There's still 5 regions that have electrons surrounding the central atom. Okay, so next one we're going to look at is ClF3. So with ClF3, a lone pair in there. Taking a moment, you can see that there are 3 bonded and 2 unbonded pairs of electrons, so a total of 5. The electron domain geometry is trigonal, bipyramidal. The bond angle will be 90 and 120 degrees. The bonding pairs are 3. The lone pairs are 2. And its molecular geometry is like a letter of the alphabet, so it is T-shaped. Okay, so that is ClF3. Now, if we look at XeF2, let me build it for you. Okay. So again, these are just models of the actual compounds. So the total number of groups of electrons are going to be 5. The electron domain geometry is going to be trigonal bipyramidal. The bond angle will be 90 degrees between the lone pair and the bonded pair. And then between the 2 bonded pairs of electrons either side of the central atom, we can see there that it is 180 degrees. The bonding pairs will be 2. Lone pairs will be 3. And the molecular geometry, again based on the unbonded pair or the bonded pairs, will be linear. So that is XeF2. So if you move on to SF6, you see there's a central atom. And go ahead and count how many domains there are surrounding the central atom. So we see that there are 6. The electron domain geometry for this is octahedral. So if I hold it up like this, you see those 4, it's going to look like it's got shape like an octahedral. The bond angle is going to be 90 degrees. The bonding pairs are 6. The lone pairs are 0. And the molecular geometry is going to be the same. Because there are 0 lone pairs. Okay, moving on. If we look at a model of BRF5, all right, there it is. So BRF5, it has a total of 5 plus 1. So it has a total of 6 domains surrounding the central atom. The electron pair geometry is going to be octahedral. The bond angle will be 90. The bonding pairs will be 5. The lone pair will be 1. And the molecular geometry will be square pyramidal. And our last model is XEF4. So with XEF4, okay. So those bonded pairs of electrons are all in one plane, and that can help you remember. There's 4 of them. So the total number of groups around the central atom are 6. The electron domain geometry is octahedral. The bond angle will be 90 degrees. Bonding pairs are 4. Lone pairs are 2. So the molecular geometry, we call that square planar. So that is a molecule of XEF4. So, shapes of molecules. Now that we have looked at the domains representing 5 and 6, let's go ahead and see if we can do a summary chart. So, trigonal bipyramidal is going to be 5 bonding pairs and 0 lone pairs. If it's seesaw, it's going to have 4 bonding and 1 lone pair. If it's T-shaped, it will have 3 and 2. If it's linear, it's going to have 2 bonding pairs and it's going to have 3 lone pairs. Octahedral will have 6 bonding pairs and 0 lone pairs. Square pyramidal will be 5 bonding and 1 lone pair. Square planar will be 4 bonding and 2 lone pairs. So again, if you write them out in this order, if you know the order, then that can help you with remembering the number of bonding pairs and lone pairs. So what was the order that we followed? First of all, we determined the total number of groups of electrons, which then provided us with figuring out what was the electron domain geometry. And from that, we could determine the bond angle. And then you were able to look at the number of bonding pairs versus lone pairs, and that gave you the molecular geometry. When there are 0 lone pairs, the electron domain geometry and the molecular geometry are going to be the same. So here is a summary chart of all the molecules that we've looked at. So we've gone from 2 groups surrounding the central atom all the way up to 6 groups broken down by bonding pairs and lone pairs. So hopefully this helps you now that you were able to see them on the screen and get that 360-degree view. So what I'd like you to do now is I'd like you to go ahead to the course Molecular Geometry and take the checkpoint quiz for lesson 1.2. So now we're moving into the final session of our live stream this evening, where we're going to discover how to draw perspective diagrams as they relate to our VSEPR theory. So when we're drawing a perspective diagram, we have to be able to represent the model in 3D. So when an atom is coming towards you, we're going to use a wedge or a triangle. And then when an atom is going away from you, we're going to use a series of dashed lines. There's a general formula that we follow. And the A is the central atom, the X are the outer atoms, and the E, I'm using it here to represent the number of lone pairs of electrons. Sometimes I see that it's written in with the letter N. So our first molecule that we're going to look at is carbon dioxide. So we see that there are 2 bonding and 0 lone pairs, giving us a total of 2 groups of electrons surrounding the central atom. So our generic formula will be AX2. Drawing it out, we have carbon and oxygen, both sides. Our double bonds between the carbons and the oxygens. our unbonded pairs of electrons on our outer atoms of oxygen. And then our bond angle will be 180 degrees. So that is a perspective diagram for AX2 using carbon dioxide. So our next, I have a model that will represent boron trifluoride. So our central atom is A, that's boron. X will be 3. So we have a total of 3 groups surrounding the central atom. Boron in the center. We're taking into account our bond angle of 120 degrees. So that will be 120 degrees surrounding between the 2 fluorine atoms. So a pair of fluorine, 120, 120, and 120. So what you also need to do is fill in the unbonded electrons on the outer atoms. So each has 2, so we have to add 6 electrons to each of our fluorines. So that is AX3, where the electron domain geometry is trigonal planar along with the molecular geometry. So now we're going to look at sulfur dioxide. So sulfur dioxide, as you can see in the chart, has 2 bonded pairs and 1 lone pair for a total of 3. So it will be AX2, and to represent that 1 lone pair, we'll use the letter E. Sulfur is in the center. Our 2 oxygens are on the outside. And the bond angle is between the oxygens. And it's going to be less than 120 degrees. And that's because of this lone pair of electrons at the top. So we'll draw a little bubble surrounding those lone pairs. And again, that pair of electrons is going to force those oxygens in the molecule to become closer to each other or further away from that lone pair. So this is trigonal planar in terms of electron domain geometry, but we call it angular in terms of its molecular geometry. That lone pair is causing that bond angle to be less than 120 degrees. So moving on to a molecule where we have 4 bonded pairs of electrons surrounding our central atom. So the generic formula would be AX4 with the bond angle of 109.5 degrees. So our carbon is in the center. We have a hydrogen here. We'll have another one here. And here we have our first time using a wedge and our dashed lines representative of the hydrogen that's moving away from you. Okay? So that's how we represent a 3D molecule for tetrahedral. So next up is nitrogen trihydride. And nitrogen trihydride, we see in our chart that there are 3 bonding and 1 lone pair. So that will be AX2, it'll be AX3E. So that will give us a total of 4 domains surrounding the central atom. Nitrogen is in the center. We'll have our lone pair at the top. We'll have a hydrogen here. We'll have a wedge. And then we'll have a series of dashed lines representing that hydrogen that's moving back. So the hydrogen is moving back. Our lone pair is at the top. Our bond angle between here and here is going to be 109.5 degrees. So that is nitrogen trihydride, where its molecular geometry is trigonal pyramidal. So sticking with 4 domains surrounding our central atom, 2 are bonded and 2 are lone pairs, so a total of 4. The generic formula is AX2E2. So when we're drawing a molecule of water, We know that our oxygen is going to go in the center. We know that there's going to be two lone pairs, so they'll go here and here. And then we'll have our other one over here. And this will be a hydrogen here. And then the other hydrogen is moving away. So our bond angle between the two hydrogens is going to be 104.5 degrees. So that is a molecule of water in terms of its perspective diagram, where we have two lone pairs and we have two bonding pairs. So take a moment. Are you able to identify what these would be? Could you write their general formula and then from that determine what the shape would be? So angular for the first one and tetrahedral for the second one. So now we're going to move on to where we have 5 domains that surround the central atom. So our generic formula will be AX5, pretty easy to remember. So our phosphorus is going to go in the center. And again, we need to represent the atoms that are in the same plane and the atoms that are basically above and below the plane. So we are going to have chlorine here, here, chlorine here, and then we have a chlorine here and one moving away from us. So filling in our unbonded electrons, on our outer atoms for each chlorine. I always advise students to go back and check that they have the right number. Don't race through them. Lots of practice. So in terms of our bond angles, which one is going to be 90 and which one is going to be 120? Well, here is 90 degrees, and then between these two will be 120 degrees. So that is a molecule of phosphorus pentachloride. Its geometry name is trigonal bipyramidal, with 5 bonding pairs surrounding the central atom. So next up we have sulfur tetrafluoride. So there's sulfur tetrafluoride. So the number of groups are 5. But we have 4 bonding and 1 lone pair, so our generic formula will be AX4E. So to draw that out, we're going to have sulfur in the center. We'll have a fluorine here. We're going to have a fluorine here. We'll have another one down here. And here's my wedge. And there's my dashed lines, and that's where my lone pair is going to be, on those dashed lines. And that's where my other fluorine is. So see how it's moving away from us as you look at it? So taking a moment there to look at the model on your screen. The lone pair is moving away. So our bond angles here are 90 degrees. And then the 120 will be between, I'm going to go between these two. Okay, so that's our 120 degrees. Now, we need to go ahead and make sure we fill in our electrons on our outer atoms. A total of 6 on each. If you want to, you could grab a highlighter and make them all a different color. Might be easier for you to visualize. So that is a molecule of sulfur tetrafluoride where we have AX4E. Now for chlorine trifluoride, we're going to have 3 bonding pairs and we're going to have 2 lone pairs. Move it over here. All right, so I'm just switching this up. Get the lone pair in. All right. So chlorine trifluoride, we have 3 bonding and 2 lone pairs. So it will be AX3E2, giving you a total of 5 domains surrounding the central atom. So to draw a molecule in terms of ClF3, in terms of its perspective diagram, here's my chlorine. And I'm going to have my fluorines here and here. And then I'll have one down here. So that's our T shape. And then we're going to have our lone pairs, one going away and one coming towards us. Okay. So remember, this is T-shaped. And you can even look at that T-shaped if I was to change colors here. All right, you see this? That looks like a T. So let's go ahead and fill in our lone pairs on our outer atoms. All right, and our bond angles are going to be 90 will be here. And our 120 will be between here and here is 120 degrees. So that is a perspective diagram for something that is T-shaped in terms of its molecular geometry. The generic formula is AX3E2. So now we're going to move on to XEF2. And we see that we have 2 bonding pairs and 3 lone pairs. So looking at the angle between our atoms, we know it's 180. So we have a total of 5 groups that surround it. So it will be AX2E3. So what goes in the center will be our Xe. Our fluorines are going to be either side, F and F. So that means everything else is going to be a lone pair. So our dash line will be a lone pair. Our wedge will have a lone pair. And now we just have 2 atoms of fluorine where we have to fill in those electrons. So that is a molecule of Xe difluoride or xenon difluoride, where we have 2 bonding pairs and we have 3 lone pairs. So again, I'm going to go ahead and show you, let's highlight like here between our atoms, that's where we're going to get 180 degrees. Now moving on to sulfur hexafluoride. So we have a central atom and we have 6 bonding pairs and we have 0 lone pairs. So that would be 6 domains surrounding my central atom. That'll be a 6. There we go. So what will be the generic formula will be AX6. So sulfur is going to go in the center. You're going to have an atom of fluorine either side. And then you're going to have one here. And your wedges here and here. So you need to make sure that you fill in the unbonded electrons on your outer atoms. So obviously it takes a little bit longer when you have 6 unbonded, or when you have 6 fluorines on the outside. So make sure that you are checking. Make sure they're separate. Okay, so that is a molecule of sulfur hexafluoride, and our bond angles are going to be 90 degrees. Next up is bromine pentafluoride. So bromine pentafluoride, I'm going to do 5 bonding and 1 lone pair for a total of 6. So that will be AX5E. So what's that going to look like? So you can see it on your screen. So our bromine is going to be in the center. Our fluorines are going to be on the outside. So our fluorines are on the outside. Dash lines either side moving away. There's our fluorines. So our bond angle will be 90. And make sure you fill in the electrons on your fluorines. Okay, so that is, and again, our bond angle is going to be 90 degrees between the outer atoms. And finally, we have xenon tetrafluoride. So xenon tetrafluoride, we have 4 bonding pairs and we have 2 lone pairs. And our shape is square planar. So again, all of our outer atoms are in the same plane. And our lone pairs, we'll fill those in. So we have a total of 6. And we have xenon tetrafluoride, so it will be AX4E2. We know that the electron domain is octahedral. Our bond angles are 90. So we'll put our XE in the center. We'll put our lone pairs up here and here. And then either side, we're going to have our fluorines. So those wedges are representing atoms that are coming towards you. The dash lines are representing atoms that are moving away from you. And don't forget to put a bubble around your lone pairs. So the bond angles are going to be 90 degrees. So that is the end of lesson 1.3. So what I'd like you to do now is go to the molecular geometry course. And you have your check for understanding quizzes. And then we're going to have a poll for our next topic. Ladies and gentlemen, thank you so much for joining me this evening. It has been my pleasure to work with you. I look forward to working with you again in the future. Please check out some upcoming videos at okellychemistry.com. Thank you so much.